Hello, welcome to my keynote. My name is Louis. I'm from Boston College, and in the research year is proudly funded by NSF. And then the topic I'm going to talk about is strongly consistent object storage across global data centers. So the outline for today is that I want to tell you what is object storage, what are some desirable properties, what are some state-of-art systems, and two of our advanced system, which is GUS, and the next one is Cholula. So what is storage? Usually we think storage is some server, like cloud server or cloud database, everyone can access it. However, if you only have a single machine, then it might crash, it might fail, then you don't have access of your data. And that's why we want to have distributed storage so that not only one server can have data, but you can replicate data to multiple servers. And in other words, you are going to have fault tolerance, meaning that if someone fails, some server fails, you can still access your data, and it's higher availability, meaning that even with some unfortunate event, you can still access your data. And usually when we talk about distributed storage nowadays, we are thinking about geo-redundancy or geo-replication. So now it's not only just servers inside one single data center. Now we are talking about multiple data center that's allocated around the globe. Why is that? The reason is that even though data center failure is very rare, but it still does happen. So we want to prevent from that. And the other thing is also, again, about higher availability, because usually if you only have one data center, you need to go far away. Suppose you are in Asia, then the data center is in America, then you don't want to pay this kind of round trip time because that it's long. So when we want to have multiple replicate data centers, then usually you can reduce the RTT, meaning that you reduce the round trip time, so you can increase performance and increase availability. And in this talk, I will focus on object storage. So what's object storage? Object is very simple. It's some data. It's abstracting. You can just have some byte, large amount of byte. An important thing is metadata. The metadata describe what's inside the object. And then the other important point is that when we store the data, we treat them as a bucket. So it's not like a file system on your computers. There's no directories. You cannot specify relationship between your data. You don't have folders. You cannot move them around. And then the other thing, the final thing is that API is extremely simple. You only have put, get, and then sometimes remove, but you don't have fancy things like typical operation that you might expect from a database. So to summarize, what's the abstraction? It's a key value pair. You have a key that specifies your data. Key is the name, and then the value is the byte, the data itself, and plus the metadata, like text description of your data. And then the support operation is that you can read, you can write, you can remove it, but you can do that only on a single object at a time. You don't do that in a batch. And then there's no transaction, meaning that you cannot touch multiple objects at the same time. And then you don't have some fancy operations like read, modify, write, compare, swap. No, you don't really have that. You only have read, write, and remove. It's very simple. However, it is still very, very useful. Large-scale web application and then your backup, like gaming application, machine learning, all use this kind of object storage. And then the reason is that nowadays we produce tons of unstructured data, like your email, video, Facebook posts, Instagram image, all those things. They are object data because they don't really relate it to each other. And then in real systems, industry use object storage to store and even process this kind of data. And if you are familiar with the industry, the cloud computing system, all the major providers use this kind of system. For example, Amazon S3, Google Cloud Storage, Microsoft Azure Blob Storage, it's all this kind of thing. Now we look at what are some important properties for this kind of distributed object storage. And then the most important property is called inconsistency. Because that this is distributed system, the clients, they can read and write at the same time. So for one data, for one key, you might have different version of the data. So in this case, this server has data version 1, this server has data version 2, and then there's a conflict. So how do we specify that? It's called consistency property. And in this talk, I'm focused on the strong consistency, meaning that the system behaves as if it's a single machine. In other words, meaning that all the observed operations, read, write, and remove, they appear in the same total ordering, even though we have multiple machines, multiple clients, they are located on different places. So again, what's strong consistency? The intuition is that you have same total ordering for everyone. And why that it's a good thing? Because that for developer, it's much easier to develop your application. You don't need to make much of reasoning because that the correctness is simpler to argue compared to other eventually consistent systems. And why is that? Because that some anomalies, some kind of incorrect business logic because of inconsistency. For this type of strongly consistent system, you don't need to care about that. And that also leads to reduced complexity. And then that's very, very important if you want to deploy the real world systems. And now again, we're focusing on geo-replicated or geo-redundant system because that we want to prevent data loss even if there's data center failure and we want to have high availability. Usually that when we do this kind of redundancy, there are two methods. The first one is geo-replication. The second one is erasure coding. Due to time constraint, like here I'm going to focus it only on geo-replication. However, both systems can be extended to support erasure coding. So now what's our desirable properties? Again, we focus on object storage, and then we focus on global data center and strongly consistent. The more formal term, more academia term is called linearizability. But for this talk, all you need to remember is that there's a total ordering. And then the final thing is that we design the system so that it has optimal commit latency. And then what it leads to practical kind of usage performance is that it will have improved tail latency. What is that? Why do we care about tail latency? And then the reason, this observation by Google, is a modern web application system. It's very complex, it's rich, it touches tons of different resources, and it's high fan out, meaning that one user observation or one web page actually depends on tons and tons of underlying operation to your storage system. And as a result, the user perceived latency, meaning that it's the tail latency of the storage. So when we design a backend system, we don't just look at the 50 percentile average or median latency. What we care about is a 99 percentile latency or even higher. So for example, right, here is some real data from Google. The median latency 1 millisecond is super good. But when we talk about tail latency, 99 percentile, it's suddenly become 10 milliseconds. And then if we do get a more stringent design, then you require all the operation to complete. Then median is 40 milliseconds, not too bad, but 99 percentile is at 140, which is not really good. Okay, so we want to design systems that have very good performance in tail latency. Then in terms of geo-redundant storage, then what it matters? Many of the real systems, they use leader-based design. So your client access the data, the closed data center, it needs to go to a leader and run some protocol and then commit the operation, meaning that I can determine the order of an operations and then get back to the client. So you have this kind of geo RTT delay, which is in the order of 200 or even 500 milliseconds. So we wouldn't want to pay that. And now the system like kind of move toward more leaderless design, meaning that you don't need to contact the leader. There's no notion of leader. So when you commit the protocol, that's what it counts. And then one important thing is optimal commit latency. So, but that I will tell you like what are some prior solution and what it means to have optimal commit latency. So what's optimal commit latency? That the notion is proposed by a bunch of people from CMU. Then the first path is that the operation can commit, like determine the operation in one round trip time. So what's commit? Meaning that after the client communicate with a simple majority of the systems, and then what does it mean to be optimal? It means that it's when there's no conflict on your operations, then it should be always on fast path. And then the group, they actually achieve like this leaderless to optimal commit latency for actually a more general system, and more general than object storage is called state machine replication. However, one missing point in their design is instant execution, which means that the operation, whenever the system, the server knows the order of the operation, it can be executed. However, ePaxos does not achieve this property. And then in that real deployment, you are going to see the penalty here. That the ePaxos is a blue line, is that it suffers low latency, even though the RTT, when you supposed to have like optimal commit latency, it should be much lower than 100 milliseconds, but for ePaxos, it's close to 300 milliseconds when we talk about tail latency. And then the GOS is our system we compare to other very closely related geo-replicated system, which is ePaxos that I just mentioned, and then also have Grief, which is an improvement based on ePaxos. Again, it's a general state machine replication. However, it does improves the read and write, and then also Giza, which is a real system by Microsoft. It's similar to GOS because it's object storage system. It supports only reads and writes and remove. And then the important analysis point here is the latency. And then the first number is the fast path. So it's 1 RTT, that's good. And then the second one is that what happens if you have conflict, that's 2. And then and here you are going to see that Grief actually does not have a good performance in write, and while the other is good. And then the other important property is called fast quorum size, meaning that how many servers that you need to communicate in order to determine the order of operation in the fast path, on the fast path. And then where F is the number of failures that you are going to tolerate. And then right, this optimal commit latency, what it means is that here for ePaxos it has both read and write, and for Grief it only has read because of the write needs to have like 2 round trip latency. And then for Giza, because the fast quorum size is too large, so it doesn't achieve any. But for GOS, it achieves both read and write, and especially there's instant execution. And one slight downside for GOS is that all this property only holds when n equal to 3 or 5, meaning that you can only replicate it to 3 or 5 data centers. However, like in industry, almost all systems only adopt 3 or 5 way replication, so that's a really good trade-off. So to sum up, what's GOS? It's a leaderless design. It has optimal commit latency, and then it has instant execution. It's the first system that achieves all these 3 properties. And then what's the techniques? The first technique is that we have speculated timestamp. It's that when prior systems, the server needs to contact other to figure out what's the timestamp. But like for us, the writer opportunistically use like the locally known timestamp as the timestamp for the operation. And in terms of that, in deployment, this is a really good trick. And then the second one is that everyone needs to communicate with each other to update their view. And then later on, they will use this view to decide or to determine the ordering of this operation. So on a very, very high level, technique 1 let us to optimistically fast write. Technique 2 leads us to optimistically fast read. And then to recap, this means that the write and read operation can be completed in one round trip after communicate with a simple majority. And so comparison, GAS is the first system that have both of optimistically fast operations and instant execution. And for ePexels, there's no instant execution. For Grief, there the write is slower. For Giza, actually the write and read are both slower. So now let's look at the evaluation. So, and then we implement GAS and our own version of Giza into the same framework of ePexels and Grief, and it's in Go. And we run our evaluation on Cloud Lab. This is the specification. And because we want to have more well-controlled latency profile, so actually we add artificial latency between machines, and we simulate three servers, one in California, the other in Virginia, and then the other one in Ireland. And then this is the same profile using Grief. Okay, and then here is the latency between different locations, and it's in milliseconds. So now the figure is called latency CDF, and then we use the same parameter as YCSVB workload, which is the most well-known benchmark for cloud storage. Here we have 3 servers, we have 2% of conflict, and mostly reoperation. And as you can see for the read here, it's almost always one RTT read because of some optimization that we can do to both GAS and Grief. And then you can see that 80%, almost 80% of latency is at this 77 millisecond because that we allocate the readers equally. And then here you can see that the GAS, the orange one, is much better than Grief for the write. And then again, this is because GAS has optimistically fast write, while Grief doesn't have that property. And then for ePexels, because you don't have like instant execution, so it's going to be slower. And then one interesting here is that this read operation, like GAS is much faster than Grief, and also here that is still faster than Grief. And then this is because we have certain re-optimization that the read can be tagged along with prior read or write, and then that's where we can beat Grief as well, even for the read. And now we look at the more scale-up system when we have 5 servers and then more conflict. And then again, this is tail latency. So this is 90 percentile, 99 percentile, 99.9 percentile. And as you can see that GAS is still much better, even though here that the optimization that we saw in the prior slide, it doesn't work now, but it's still faster because of better design. And then what happens if you want to write it to the disk? Then it's a durable write. Every write is a durable write to the SSD. Then even with this longer latency, the GAS still has a better latency in both like normal latency and tail latency. And now let's look at our second system. It's Cholula. It's an off-chain storage. So now we switch context a little bit. It's on blockchain. So what's blockchain? It's decentralized, fault-tolerant, and secure, and it's a way of like coordinating or sharing and storing information. And now we are talking about on-chain and off-chain storage. So for on-chain, data is stored inside the blockchain. Off-chain is that you have like data stored in external storage. And the reason we are going to do off-chain is that even though now it's kind of crypto winter, but it's still so expensive to store large amount of data on-chain. So that's why we want to do off-chain. And then here we have our system. It's fast, it's fault-tolerant, it's strongly consistent. And then again, we look at object storage system. And then the fast is that we have similar design that we can have optimistically fast operation. And then here we make it more robust so it can tolerate Byzantine failure, meaning that the Byzantine server can do arbitrary thing. And then again, we have strong consistency, meaning all the operations follows the same total ordering. So here the key thing is about our metadata. So our metadata store like lots of different things that we can use, implement fastpack souls like efficiently. So phase one is the same as fastpack souls. That's nothing new here. And then the key thing is that we observe that in the common case, most cases in phase one, and then you only need to do coordination under some edge cases, and their client actually can do this much more efficiently. So now again, for evaluation, we compare with Giza, and then we compare real system Cassandra, and then everything is also in Go, and now everything is like stored inside the Cassandra as a backend. Just a coordination protocol is different, and again with like benchmark in Cloud Lab. And because we focus on the common case, so there's no context, so everything goes through the first phase only. And now here is the latency profile similar to before. And here the Giza is a green one, Cholula is our system is the blue one, and Cassandra is the orange one. As you can see, Cassandra is slowest because that the coordination protocol is not very it's not very efficient. However, Cholula has a latency much better, like almost 13 milliseconds better than Giza, and then that's because that we have a smaller quorum size, and then that turns out to be key in how we can achieve faster latency. So to summarize, hopefully that you get an idea of the importance and property for object storage. And we have two very nice systems. First is Gus. We have this optimistically fast read and write. And then we have Cholula. We have advanced design that we can do efficient operation off-chain. So what's the take-home message? Take-home message is that you want to be very, very careful when you choose your system. So even for like something simple like object storage, you say, hey, just key value store, how hard is that? It turned out that it's still very difficult to find the right balance between performance and fault tolerance. All right, so that's all for my talk. If you have any questions, feel free to email me. Thank you.